we actually have dual independent engines, and down the road it'll probably be more than dual engines, basically guaranteeing that we can saturate the bus at all times to data transfers while not locking down the GPU. And that wasn't something we had prior to G80. And G80 started down this road, but Fermi pushes it much further down the road. And it's just kind of emphasizing that memory is really important. So this is just kind of a quick recap of where things have been moving. I won't spend a lot of time on it, but 3 billion transistors for Riva back in the day, 3 billion for Fermi today. So a lot more powerful and a lot more general.
So you mentioned earlier that the different cores are no longer, each step is independent, so like a particular set of vertices can take a lot longer to shade.
It used to be that you were stuck with a certain number of instructions. Now it can be arbitrarily long. You could program a shader that would take a day to run. The driver is usually going to have a problem with that. We're usually going to think, oh boy, you're hard. But with some specialized work, you can do it.
Yeah, it seems like you're going to be stuck on, if you're trying to render a frame, then whatever your slowest part of that pipeline, no matter what, even if you can render 3/4 of the frame really quickly, if you have to stop on a single part to do advanced work, that's going to hang your entire
absolutely. And game programmers are very plan ahead sort of people. So when they ship a game, they ship something that will work okay on a mid-range chip, maybe even on a low-end chip. And on the highest-end chip available at the time they ship, they're going to have some setting that will top out at 30 FPS. And for years afterwards, there will be guys out there that are trying to tweak it to get to like 200 FPS with whatever the game is. But what they'll do is they'll actually have adaptive code that will, it'll say, oh yeah, I know I'm on this GPU, so these features are available, et cetera, et cetera, et cetera. They'll have stuff that'll try, that'll test it out. They'll send workloads down and see how long the workloads take to complete, and they'll adjust the shader based on what they think the GPU can do, so that they guarantee a certain throughput and frame rate. And they'll keep adding more and more cool effects and more nifty things until the GPU just can't take it anymore. So that, and then the other side of it, for people doing oil and gas exploration or medical imaging and stuff like that, they don't really care about frame rate. They're trying to just get the most computation they can, and so then for a general purpose compute unit, that's great. But any other questions? Yeah.
Yeah. So how well does the GPU work together with traditional graphics programming? Can you do both at the same time?
Yes. You can do both at the same time. They both use the same basic cores, so they're going to be somewhat competing with each other. And they also share the same video memory, so they're going to be competing with each other, but they can work together. Now, as I say that, I know for sure in Fermi that they can run, that the compute engine and the graphics engine can run completely concurrently in parallel. I'm pretty sure that's the case as far back as at least early on in the G80 life time. I won't guarantee that that happened on actual G80, but it's not uncommon to have compute go do some chunk of work completely independent of graphics, and then when it's done, graphics will take the result and work with it. So when you hear about PhysX or things like that, that's kind of, PhysX is using compute alongside graphics to cooperate. And then there's a lot of extensions going on for interoperability between OpenGL and OpenCL, or direct compute and DirectX, so that you can really finely interleave what you're doing. And actually, I'll hint a little bit at the end where things are going hardware-wise, but that's an important thing. You have a question?
I was just kind of curious. You just mentioned PhysX. How would this interact with like a physics card, or would it like replace it entirely?
So our hardware itself doesn't have any explicit interaction with a dedicated physics card. You're probably talking like AGIA or some of the stuff they're doing.
I don't remember. I just remember there was a dedicated physics card.
Yeah, so I mean, we don't explicitly cooperate with any sort of dedicated physics hardware, but this basically is our way of saying, hey, you don't need dedicated physics hardware. You've already got a really massively parallel system in there it's pretty generalized, you can use this for physics. And obviously, for certain really specialized physics things, you can, there's always that trade-off, right, between fixed functionality and general purpose. And so if you have something really specialized physics-wise, you know, maybe some sort of computational fluid flow, or, you know, I'm not sure what's in some of these physics cards, but they might be able to beat us at very specific things. But to do general purpose physics, I think they're going to have a hard time making money going up against us, just because we can do a lot of things and we can do physics really well. And so they have to do physics so much better than us with this specialized hardware to make it worth spending that extra money. All right. I keep talking about throughput, but I really want to explicitly say throughput here. This is really the key, because any individual core in the GPU is not as powerful as any individual core in the CPU. And our latencies are going to probably be higher. Switching off what these cores are doing, accesses to textures, accesses across the bus. But you can hide that latency by having a whole lot of cores doing all kinds of things with things buffered up between them. So if any one operation takes a little while, but all those, you can have all of that latency hidden by doing a ton of these operations all at once. That's throughput for you, and we can get a lot higher throughput than a CPU can, and that's, for the foreseeable future, that's going to be true. So if you can find a way to get a lot of threads running, and I don't know what we're currently saying for CUDA, but I think it's not uncommon to say people are using 10,000 threads at once, essentially. Now obviously we only have 512 cores in Fermi, so they're not really all running at once, but they're essentially all in flight and all scheduled and all going to be running essentially together. So that's a lot of concurrency. What that means is that you have to find tasks that fit that sort of parallelism, and I'll talk about in a little bit what's appropriate for a GPU and what's not. But yeah, that's the basic idea for GPU parallelism. So GPU computing, it started a while back, basically with GPU stuff. 2003 was really where it started happening. And I won't harp on this too much because you guys all pretty much know this, but GPU is hard. I mean, if you guys have ever tried to sit down and do it the old way, shoehorning general purpose algorithms and logic into a graphics way of thinking, it's really hard. So more evangelism, I'm going to kind of skip through, and we've talked about all of this really. Actually, I will say, before I get on to exactly where GPU came from, I will say this, that by doing parallel algorithms right, with the right hardware and the right memory layout, you can get really disgusting speedups. Like, these are good, right? That's pretty good. If you can go from basically taking a week to taking half an hour to get your results, that changes the way you do things. And there's a lot of examples of this, but basically the takeaway is this changes the way you do things. It's not just a, gee, we're twice as fast, that's cool. This is, oh wow, we can actually do things now that we would have never thought of doing before because now we can do this so fast. These are just kind of some examples of things that come through. You know, this is pretty staggering to get 146 times speed up going from a highly optimized CPU implementation to a highly optimized GPU implementation. Now these aren't naive implementations. These aren't guys that just said, oh hey, I'm going to port my Fortran application over to the GPU and be done with it. They spent a lot of time working on this. They didn't start at 100